using the pads.
Oh.
The pads recovering pads. Yeah.
Oh, okay. So what did you do?
We were just trying to reverse it.
So you constructed one
All right, welcome back. Don't be alarmed. So our next lecture has the hardest task of this summer school, because so far everything was about thermodynamics, and Ladina will have the task of introducing a completely different subject, black holes, and she has 3 hours to tell you, to give like a minimal description to black holes, assuming that you don't even know anything about general relativity, and then she'll talk about thermodynamics of black holes. Ladina is an excellent researcher at ETH. She's also a first-year PhD student. First month PhD student. And she's excellent. She gives beautiful talks, and I'll be doing very, very heavy sharing here so that to allow us to get somewhere. Okay. So there's some additional rules for this talks, and these are the rules. If you have a PhD, not allowed questions out loud until the end of the lecture. At the end of each lecture, you can ask questions. If you know about black holes, and your questions are just comments or how does this relate to that, no questions. Wait, try to understand, follow the lecture notes that Ladina posted on the website, follow the references within, and you can ask at the end. Okay? Questions are sentences that start with something like what and how, not I think, or I disagree. Okay, these are not questions, they are comments at the end. Okay. Finally, because sometimes things are a bit abstract, and if you just give it 5 minutes, Ladina gives an example, and then everything becomes more clear, right? So if you have a question that is about like not understanding exactly how this concept fits, just give it 1 minute. Or ask the person next to you. Okay, we very much encourage asking the person next to you. And then if it's still not clear after a minute or so, then you can ask the question. Okay, so I talked to Ladina, and first we completely change of topics and we do black holes introduction. And then we pick up on where Renato left and do it right there. Okay, so it's a pleasure to introduce Ladina Hausmann from the THC.
Okay, so as you said, I'll start with black holes, and don't worry if I write something on the board and you don't like understand what each part of the formula means. Sometimes it's only for completeness and will only look at part of it. Yeah, and otherwise, we'll only use certain parts, so don't worry. And maybe just if you can't read, also. So we'll start out with the Schwarzschild metric, or the solution to a spherically symmetric mass, in particular non-rotating black hole. And I'll just write it down first. So now this might look big and scary, but just to
Can you write it even bigger?
even bigger. Okay.
This is sigma, yes?
No, there is an R. This is an R. There's no sigma.
Okay.
There's a theta and a phi. So we have here the g, which is just the gravitational constant, and m, which for the moment actually is only a parameter of the solution. So they're just different kinds of solutions. But it will turn out to, in the end, be the mass of the body we look at. And if you, for example, just consider how a test mass very far away from this black hole moves, we actually just recover the Newtonian equation of motions. We all already know. So now, if you look at this equation, you see that at 2 points it has a problem. So at 1 point, it has a problem when r is equal to 0, and when r is equal to 2gm. So if metrics in GR have a problem, there are two places this problems can come from. So we have problems, or and these problems are at r is equal to 0 and at r is equal to 2g. And the two ways a problem can come from is either that we have a singularity, and which is what we expect with a black hole, or that we just chose bad coordinates. So I can be very creative and choose coordinates for actually flight space that become singular if I'm creative, but then I just chose terrible coordinates. And here we actually get both cases. So here we have a singularity. And here we have just bad coordinates. And if you want to know what different coordinates to choose, there's a reference in my lecture notes, how to choose good coordinates in this region. So even though here we just chose bad coordinates and nothing terrible happens, you still notice that the metric, the time part and the space part change sign, because if r is smaller than 2gm, this
Can you just raise the bracket so we can see it?
So if the time part, if r is smaller than 2gm, it becomes positive, while this becomes negative. And intuitively, one can see this, that then time and space kind of swap their roles, and one can no longer stop falling into the black hole, just as you cannot stop currently moving in time. So what we find is that here we have we find that at r equals 2gm, we have an event horizon. So if you fall into, or if you fall further than r equals 2gm, you can no longer escape, and you're doomed to fall into the singularity. And then we can consider another feature of the metric. I guess I'll swap board. And that is the gravitational redshift. So if you can insert the metric, you see that the this prefactor here for R getting closer and closer to GM gets smaller and smaller, which means that factor or unit of coordinate time will account for less and less proper time. So what this means, if I'm at infinity and I have someone close to the black hole sending out a light ray, this light ray will oscillate for me slower than for maybe Alice close to the black hole. So this means that for me, when the signal reaches me, will have a will be redder than for Alice. So what this means is that there is a redshift for me. So for me at infinity, I'm somewhere very far away. I see her redder, and if you want to have some formula, if this here has energy E for Alice, for me it will have energy. It will have energy. R is where Alice is. So now we've considered just black holes that can't rotate and then also can't have charge, but Renato mentioned before that we also can look at these. So let's do this, and for this we again need a different metric. Maybe I'll clean this board so I have time to write it down. Later, when we consider thermodynamic processes, we will notice that it is very useful to actually look at rotating black holes because we can do more things with them. So now I just write down a different metric, which is called the Kerr-Newman metric. Which is longer, but so where these sigma and delta are just actually shorthands to make this metric not even longer. So now we do kind of the same analysis again as we did before. we have again 2 points where this metric can become problematic. So we have the point where the sigma is equal to 0, because then all of these denominators are 0, and then we have the point where delta is equal to 0, because this denominator becomes 0, and this here is again actually the singularity. This here is again just bad coordinates.
Can you maybe just say when to use one metric and when?
So they are actually the same. If you, I forgot to mention this. That's a bit wrong by Lydia. If I have A, which is actually just a parameter, but can be seen as the angular momentum, and E, the charge of the black hole, are 0, then and you set it to 0 everywhere, you actually get this Schwarzschild metric back. So this is really just a kind of a generalization of what we had before. So we're looking at the more general class of solutions. As you see, or as you might suspect, this is no longer strictly symmetric, because here you have kind of the metric of the sphere, and here you don't have this term anymore, because it's no longer strictly symmetric, because you have this rotation. So very intuitively, it rotates around an axis, so you're no longer sure.
There's a question?
Could you quickly repeat what A and what E is?
A is the kind of the angular momentum over the mass, and E is yeah. So let's further discuss this. Let's further discuss these two problematic points. Exactly, one is a singularity, and the other are just bad coordinates. And people might be concerned that this is only a singularity when theta is actually, or the cosine of theta is 0. But I can show that this is actually, you can approach from all directions and you still get a singularity, so you don't have this weird thing. So don't be worried about that. That's also not. So the reason this metric is so useful later is because it has another feature called the ergosphere. So one can define energies of particles as seen from infinity, which is conserved in collisions and also later than splits, and also along freely moving, or when they're freely moving. And in this ergosphere, this energy can become negative. This ergosphere is it's given by R plus, which is the event horizon, and this so we have a region. So this is kind of the event horizon of the black hole. So this is the lower bound of R. And here we have, because of the cosine, kind of these two lobes on the side, and the black hole is spinning around this axis, where the energy of these particles, as seen from infinity, will be very important later for processes we consider with thermodynamic processes, because then so now what helped me when I was reading into this were so-called Penrose diagrams. So diagrams.
So a small question, but the delta equals 0, is it also can be interpreted as the event horizon?
Yeah. I forgot to say this.
So you have two different R,
So it's the R plus is the
only one. And thank you.
So what helped me understand this a bit better is Penrose diagrams, which help to kind of see the causal structure of space time, so event horizons and singularities. So for this, we first kind of distort space-time, or we distort it such that we can draw it on a blackboard, so it's particular finitely sized. And you can do it because if you distort the metric in the right way, light rays stay the same, and kind of space-like and time-like notions also stay the same. So first, it's kind of an introduction to this. We just consider Minkowski space, so flat space, which we all know, and we look at it in spherical coordinates, because we also need to get rid of two coordinates so I can get it on the two-dimensional board. So I just write down the metric in
On the plot, is it one ellipse and one sphere, or the two are?
so it's like just what you get from here. So it's kind of a ellipse. I'm not sure if it's technically an ellipse, but it's like a sphere inside an ellipse, and this is the ergosphere. Does this make sense? So I was writing down the metric for Minkowski space. Spherical coordinates. Right here, this is just the spherical part we also saw in the Schwarzschild metric. It's going to be very unimportant in this diagram. Because what I do is I first have to get rid of these two coordinates, and I do this by just ignoring at each point the two sphere, because it's spherically symmetric anyway, so I don't really, doesn't give me much information, so I kind of get rid of it. Well, I still have the problem is that T is in R and R is in R plus, or R bigger than 0. So I still can't draw this on the board, it's still too big. So I can do a coordinate transformation, and I do this. I define big R and big T, capital R, as the arctangents of the small, or the sum of these as the arctangents of the sum, and the same with the difference. This, because of how the arctangents work, or how the arctangents looks like, it takes me the real line, which I get here. So which I will have here, because C can be anything and R can be positive, to plus and minus pi. So the new coordinate ranges are such that T plus R is just smaller than pi over 2, which is very much finite, and R has to be bigger than that. So these coordinates I can very much draw on the board, because they're just, pi is very small. So what is this? So I can draw this just as this triangle with 45-degree angles. Like this, where kind of here is time, this is the. And then you can typically label these points. So this is called the past infinity, and this is the future actually time-like infinity. This is the space-like infinity, so this is kind of infinitely large. And then we have the null infinities, or where light rays start. So maybe it becomes a bit clearer when I draw in different things. So a massive particle would start out at the past time-like infinity, travel somehow up, and then end its life or end its future infinity. A light ray would start out somewhere on this null infinity, and then always travel on 45-degree angles because we distorted. We changed coordinates such that light rays stay light rays or stay on 45-degree angles, and it moves to the future null infinity. So you kind of see here also that there are no event horizon. Every light ray can always go to the future infinity. Every particle could also, there's no point where it can no longer escape to its future infinity. So as one would expect, this is actually represented. And now for black holes, we can do the same thing. So here I won't do the entire derivation, but what one gets is this kind of diagram. Here we have the singularity. So we have these. And on the other side, the same. So here you notice that this property of that everything can always escape to the infinity no longer holds. So if I am someone sends out the light ray from here, there is no way this light ray can actually go to infinity. It has to always end up at the singularity. Whereas here, depending on which way the light ray is shot out, I can either go to the singularity or to the instant. So and here is kind of the event horizon, because if I pass here, I can no longer escape to infinity, even if I travel at the speed. Because the metric is time reversal symmetric, so you can reverse time and select the same thing. You get the opposite of a black hole too, which is a white hole. So where you can also observe what light rays can do is they can only escape. So I can either escape to this side or to this side, but they can not get back. And all light rays that come to this point must have come from the singularity, and they can't come from another event. This kind of explains this circle.
Can you speak a bit louder? Sorry, the camera is always running away because outside was louder than you.
Okay, so I'll try to speak louder. And the point of the problem with kind of this thing is this assumes that the black hole has always existed and will exist till forever, which is not realistic. Black holes we find in the universe have typically come from, for example, stellar collapse or something. So at some point there was a star which is not a black hole, and then there was a black hole. But because stellar collapse is kind of complicated and not every star can collapse into a black hole, we just look at something very simple. We look at a shell, so a spherical shell of light that is moving inwards. And we're trying to kind of, out of these two diagrams, piece together the space-time diagram of this situation. So what we have inside the shell, we just have a normal flat space because we're inside a spherically symmetric body. So we have this normal space. Outside, we will have the Schwarzschild solution because, as I said, it's very general. It doesn't only hold for black holes, also for the Earth, which is spherically symmetric, has the same solution outside of the Earth. Inside something else will happen. So what we then have to do outside, we have to put in the Schwarzschild solution. So like this. So we piece together part of the Schwarzschild solution and part of the Minkowski solution. And this line here I drew is actually the spherically imploding. So it moves on a 45-degree angle because it's light, and inside we have the Minkowski space, and outside we have Schwarzschild solution. And now we can ask ourselves, where is the event horizon? And that's just the point from where I can no longer escape to the future infinity, which would be here for space light and here for light. So I can no longer do this once a light ray can no longer reach it. So this would be this one. Because you can just think about it, if you are here, light can only go to singularity, whereas if you're, for example, here, you can still So the kind of the remarkable thing of this is that even if you're still in flat space, you can still already be in the black hole, or in the event horizon. So being in the event horizon, or actually also crossing the event horizon, is nothing. You will not notice anything. So you can even be inside already and you don't know, and there's no way of us knowing. So
You have 10 minutes.
10 minutes. So then we can already start discussing black holes. As thermodynamic objects. So sometimes, or also what we just did before, we looked at the black hole just as a region in space-time where you could no longer reach the future infinity. Yeah?
So just understanding. So can you explain this again with the imploding shell? So like where does what come from? When do you get the black hole?
So you have an imploding shell. So imagine an imploding shell of light that's moving inwards. Mm-hmm. So this travels on 45-degree angles in your diagram, and inside of the shell, you'll have flat space because you're in a spherically symmetric mass, so you have everything cancels out. So inside of this, you have flat space. So what we draw is inside. So this is the boundary. It's the shell, and inside we just draw the Minkowski space diagram. And outside of it, or of all spherically symmetric bodies, you have the Schwarzschild solution. On Earth, you will not have a singularity because Earth has a radius which is very large compared to the Schwarzschild radius. But so we can just stitch these two together. So we sew them together at kind of boundary, which is the slide shell. So I draw outside here. I draw the Schwarzschild solution. So then I don't have kind of the event horizon yet. So that was kind of drawn in later. And what you then can do is you think about, like, on each point, can a light ray reach the future infinity or can it not? And if you think about this, you notice that this is really this 45-degree line in the other directions. Is it clear now? Or?
Yeah, thank you.
So let's come back to the stuff I started. So I mentioned that we looked at as black holes as really a region in space-time which where we're pointing where light can no longer reach the future. So it's a space-time region which in particular cannot really evolve in time. It doesn't really make sense to find having an initial and final state, which is what we need if we want to apply the framework. So we kind of need to do something different, or we need to formalize a bit the intuitive notion of throwing something in the black hole and then it's growing a bit. So what is then often done is one considers the black hole, and then one Planck length away from it, one considers a surface, which is then just an ordinary kind of surface which can evolve in time, and it's effectively also a surface where you can only enter, because to exit it again, if you remember back to the energy, to the redshift, to exit again, you need very, very high energies, which are actually Planck scale. So all the physics we understand is really outside of this. So what we then in the future will implicitly do, we will always consider the evolution of this surface in time. And interestingly, this surface, which is sometimes called the stretched horizon, if you assign it like physical properties, which are purely ideas, like it's conductive, it's a viscous fluid, and you make it such that it looks like, or the charge and stuff looks like from the outside as if it were from the black hole, you can actually derive certain things which you can, and the results are correct. So now that we know what it is, let us look at the state space. So in GR, there's this thing called the no-hair conjecture, so that the black hole doesn't have hair, which just means I can only describe it by these three parameters: M, L, which is just this A we had from before, and Q, which is just a new name for the E we had before. And for these to be for the black hole not to have too much angular momentum compared to its energy, we need to impose this restriction on the parameters. And one can actually formally define the energy, the angular momentum of a black hole. It's very complicated. as an integral over this future space-time infinity. And the resulting quantities are also just these parameters. And as space-time in the end, or if we are very far away from the black hole, it becomes flat. So you can actually consider these as conserved. So we can work with an energy conservation law. So I think now would be a good time to end.
Okay, so far we have this complicated background for the metrics and everything that allows us to derive the black holes, and then the only thing we'll use from now on is this three properties:
Yes.
mass, angular momentum,
And we
and
will
charge.
use that they're conserved. So that's
Yes.
And we will use that there's an event horizon and that there is this ergosphere where energies can be negative. And yeah, that's
Yes. So even if it was hard to follow the geometric part, then the rest will be now very simple from now.
yes, we will only use these few simple properties of the black hole. Yeah. Do you have a question?
So there's no hair theorem. Like to which extent do these parameters fix the black hole? I mean, like if I have a black hole and I have outside, I have some masses floating around, like I have a black hole and I have some mass somewhere else. I mean, the mass of the black hole, the angular momentum, the charge is all the same, but it's a different metric, obviously.
Yeah.
Like,
So we assume they're just very small and very far away. Like we assume they're non-interacting.
yeah, yes, yeah, yeah. I mean, I don't quite get, like you say these three parameters, and you say these uniquely distinguish what, like a metric.
Yes,
a
so these
metric
uniquely
or-
distinguish all stationary solutions of basically all kinds of black hole. If you have a particle very far away, your metric will be slightly different.
Yeah.
But that's also no longer a different situation. But in our discussion, this particle will be very light, so or will be very far away, so we can kind of isolate the region.
Can you explain maybe again why the energies can be negative in the ergosphere, or what this means exactly?
So it's kind of more complicated, or it's not so easy to explain, but the basic idea, or maybe two ideas, if these particles can then no longer, if you have negative energy, you have to fall into the black hole, and then these extract. So then if you look at energy conservation, the black hole will lose mass, and these extract then angular momentum from the black hole. So you kind of take rotational energy out of it. So that's maybe the intuitive.
Sorry, can you explain again why do we need to impose a restriction on the parameters and they are not free?
So if you just look at angular momentum, it's maybe easier. So you have a non-charged one. If angular momentum would be too large, so you will get problems with the metric then. But intuitively, you just have too much rotational energy for the mass.
Okay. Does this have a consequence? I mean, like this cannot happen in the sense that it's not a physical situation, or is it a convenient?
So I think if you would violate this, you would get like a naked singularity. So you get a singularity without an event horizon.
Okay. Okay.
And if you have a collapsing like shell or something like that, it will then settle down to such a metric. Okay. And do we know something about the speed or? Okay.
Sorry, what was the question?
If you have a collapsing, that will if it will settle down, and we assume it already like it collapsed long time ago.
Then we go for lunch, have a break here, and we come back at 1:30. Thank you, Ladina.